Thank you all for coming. Today I'll be talking about MarkAML, an automated framework for malware hunting. I'm Pham from Spylabs. So the reason why we implemented MarkAML, we see that Marco's market share is increasing. It made up about 9% in total operating system share. And there's an increasing number of new malware. It has grown 700% in 2016. And more than 700,000 instances in 2017. Also, increasing complexity of mark threats. We already heard on the news that there are more and more advanced persistent threats, evasive malware on Mac, and even ransomware on Mac. And there's a lot of automated solution done for malware hunting on Windows or Linux and even Android, but nobody ever talks about Mac. And common techniques to analyze malware using sandbox technology are not well developed on Mac OS, and therefore it motivates us to develop a modern malware analysis framework on Mac. And our solution is to automate as much as the interactive analysis as possible and produce analysis reports describing exactly what it does when it runs, and specifically allow us to perform a detailed analysis without any human interaction. So, common malware analysis techniques for Mac are static analysis and dynamic analysis. However, signature-based approaches have shortcomings given the quality and quantity of today's malware. And hybrid analysis are widely accepted solution to cope with the issue. And we evaluated a number of malware analysis solutions, such as Cuckoo Sandbox, VirusTotal Apple Sandbox, FireEye Mac Monitor. And eventually, we chose Cuckoo Sandbox, where Cuckoo Sandbox is an open source software for automating analysis of suspicious files, and it uses modular components to monitor the behavior of malicious process while running in an isolated environment. So the very first thing is static analysis. We implemented that feature by gathering feature information from Mocho binary, just similar to other binary malware analysis platform. So we gathered header file, code, data segments, shared libraries, load commands, and symbol table. For each of the segment in Mocho binary, we extract information about the section, and then we calculate the segment entropy to detect pack or encrypted access. And another information collected and potentially significant for analysis is the code signing certificate, which can lead a malware to an indicator of compromise. And it would be very helpful for analysts to hunt other samples sharing the same certificate. And from malware author's point of view, code signing is very important for them because it's nearly impossible for ordinary victims to execute unsigned binaries because of the gatekeeper from macOS Sierra. And a large number of software on Mac mostly take the form of BSD style, where the packages store within a OS X specific disk image, .img or .dmg, and or Mac application files, .app. And the package contains other resources, including significant information, for example, the property list, the plist. And that plist are the XML-based files used to store the application configuration. And we extract and store these results that can provide a very good starting point for investigating suspicious files. About the dynamic analysis, here is an overview design of our MarkAML dynamic analysis. And it can be divided into two main parts, the host analysis machine and the monitor machine. On the right side of the screen, this is the analysis machine which builds upon the Cuckoo Sandbox, the Cuckoo front end. And it has a web panel to interact with analysts, and it stores the reports, the storage. It also supports Elasticsearch as well as Yara and VirusTotal query. And there's an analyzer responsible for sample distribution, and it does behavior analysis and behavior signature. And it can send the samples to multiple monitor machine. And in the monitor machine in the left side, the malware basically running on the user space. And in the user space, there's an analysis agent to receive samples from the analysis machine, and is also communicate with the kernel space. On the kernel space, where we implement our kernel space monitor, and it can monitor the system calls, can monitor process execution, file operation, or network activities. And Cuckoo supports many virtualization miniatures, and we successfully created virtualized Mac instances on VMware, on VirtualBox, and on QEMU, so that the analysis machine can be on whatever operating system you want, but the virtualized machine must be running on Mac OS. And by the way, any sample types are supported as long as there are software running on the monitor machine supported. The reason why I mentioned about this because ISO method for debugging and monitoring processes is basically you start a program and then immediately you instrument to that program. But it sometimes fails because of the Mac sandbox policy. And in our solution, the sample is executed by the open application. There's a default file handler on Mac. And its mechanism is similar to how user open a file by a double click on it. And then the program will decide which kind of application to open, and it supports almost any file types. Therefore, samples could be Office document, can be PDF document, or an Apple script. But the trouble for this double click is that open spawns a new process, and it goes to the Mark Cisco interface. Mark in here is the mandatory access control framework, and if you try to hook it in the user space, then normally it will fail because it's supposed to be checked by the Mac sandbox, and probably it will be rejected, but we still need the process tray anyway in order to do the behavior tracing. Fortunately, with the help of hooking system calls in the kernel space, and that sandbox mechanism doesn't affect our solution, and then Malware framework can trace process spawn to the open, to launch to XPC process services properly, while the trace and Mac Cuckoo sandbox easily failed. And other archives like the Apple disk image, we firstly attach it via HDI util, and then we execute all the application inside the attached volumes. For cross-platform malware variants, using scripting application like Java, like Perl or Python, then we use their own interpreter to monitor their behavior. And about our kernel space monitor, it is motivated by previous research on Onyx Black Cat by Pedro Vilaca for kernel system code table discovery, and Grey Fox by Vincent van Michem. And firstly, Mark Kemal solved the KS error, and then it deactivates the kernel memory protection. And the monitoring happened by hooking into a set of system calls for extracting the behavior information. And that set of system call can be customized by the analyst. And that module will intercept the system calls and collect corresponding arguments. And therefore, it is possible to collect drop files while running the binaries. And by tracing the process tree and the XPC service messages, it helps to find the shell commands, suspicious network activity, and file access behavior. For example, a malware tries to open a network port, and if no communication established, right, there won't be anything captured by the network sniffer. But using our solution, obviously we can see that kind of listening port activity while we're looking inside the network system call log. And also, Mark Kemal is able to detect evasive technique and mitigate them. Common anti-debug techniques are calling the ptrace or calling the system control system calls to detect the debugging flags. And this kind of tricks won't influence our kernel monitor components like Mark Kemal. However, it will intercept and report these activities for later investigation. And for anti-sandbox mitigation, it not only hook, but also patch inside the kernel memory on the fly to manipulate the return values. The goal is that we are gonna cheat the malware that we are running on a physical machine instead of a virtualized machine. For example, the system integrity protection status, process names, virtual device information such as the display resolution, virtual device information like the number of processor cores, the model name of the device. We also patch all of that. And we do patch the configuration of the monitor machine to mitigate the techniques. For instance, to patch the CPU ID or the virtual MAC address footprint. And during the analysis, the sandbox implements libraries for taking screenshot of the desktop. And these screenshots are very helpful for analysts to review automated analysis and recognize some cases that need human interaction. For example, like you need a mouse click to confirm installation, or you need to type password for super user privilege. And on the left side of the screen, this is the authorization solver, which automatically type the super user password when needed, and is use a Quartz library to detect login window and then answer password using a keyboard events. In the right side of the screen, this is also use the Quartz library to take the screenshot, and then we search for needle in the haystack. For buttons, we need, for example, the OK, continue, next, or done button, and so on. And then the software perform a mouse click by using the Quartz mouse event. And now that we have seen how the malware works, I'd like to show you how to hunt real malware in the wild. So by testing our framework, we found Mugdasec, which was an example of how we found malware by using our framework in the wild. Some of the samples were first discovered by Malwarebytes and Patrick Wardo from Objective-C in the last August. And by testing on the framework, we discovered more than 100 of signed malicious binary in the wild belongs to the whole adware campaign. And we constructed a powerful signature that combining static, dynamic, and network information to detect malware. And by noticing the suspicious behaviors such as the malware trying to do evasion technique by detecting the network driver MAC address to see like whether or not you're running on a physical machine or a virtualized machine. Also, we noticed a signature that they plant a persistent indicator, namely mugdasec.plist. We also construct a set of network suspicious domain, and we construct a static analysis that we see the developer code signers, mostly of the campaign, using a Vietnamese code signer name. And the interesting fact is that the whole campaign stay undetected for at least 3 months before Apple revoke those certificates and silently release an update URL rule for their export tag. And on a large scale, we have processed more than 2,000 malicious samples, and we found that 85% of the collected samples are adware, which dominated by OSX Pirate and OSX Markkeeper. And their purpose is to make advertising revenue for attacker by installing potential unwanted application or potential harmful application, or redirect the victims to unwanted website. And in my opinion, they are widespread because technically they are not virus, but it can potentially perform malicious activity later on. And after analyzing the sample set, the results retrieved from MarkerMal were later post-processed through a classifier based on hybrid rules. And so far, we observed a total of 86 different malware families until 2017. And we found that half of them belong to backdoor and Trojan. And by picking out Marco's malware family, we have selected 2 sets of malware in 2016 and 2017. And here are the heat maps where the reddish color is larger values and the smaller values are displayed by lighter color. And 2 heat maps has been constructed with featuring behavior on the horizontal axis and the malware variant names on vertical axis. And we see that macOS malware in 2017 demonstrate a drastic improvement by using anti-analytics techniques, including anti-debug, hibernation, discover hardware specification, or discover security tools running on the victim machine. Previous research in the field claimed that malware can be detected by using bash shell commands detection or persistent attempt detection. But however, we found that some variants never exhibit any persistent attempt or shell commands such as Ocean Lotus, H-Agent, or K-Ranger. And H-Agent and Complex are known for participating in APT28, targeting individuals in the aerospace industry. So that, in conclusion, we think that it is possible to automatically monitor and analyze network traffic, malware evasion techniques, persistent methods, file operation from samples in a virtualized Mac environment. And we succeeded in clarifying malware variants and its evolution on macOS. And we found an undiscovered malware campaign, including legitimate Apple developer certificates. We found other undetected backdoor belong to APT32 Ocean Lotus, targeting Vietnamese and Chinese organizations. And the framework is up on GitHub. I hope one of you in here could take a look at my code and do something even better than this. And if you're interested in improving this work, I think there would be a lot of things to improve in here. And I definitely don't think that my solution is the best solution for Mac malware hunting. But I think like at the moment, it's possible that our solution is outperforming existing open solution at the moment. And for future work, it would be interesting to see MacML combined with machine learning or bare metal analysis and API calls monitor. So thanks. It's time for Q&A. So I think that's it. Thanks for joining me.